There are kind of our rules. We get our rules up at the top. Our acids and esters are the two big ones that you're going to be kind of needing for extra nomenclature rules. You'll notice that there aren't parentheticals next to either of those. What does that mean?
They'll never be together.
They'll never be together. Why? Why do we have the parentheses? What was the point of the parentheses?
To show if one of them was the first in the...
Which means we don't have the rule set, at least off of my summary slide, to have a functional group or have a structure that has both an acid and an ester in it. Because if we had that, one of them has to take priority over the other. I would have to address the name accordingly. Make sense? Okay. So there we go, one little bright ray of hope. We don't get something that complex. Yay! Like, count your blessings, right? Okay. So let's take a look at the ester first. We have this O8. Right, so if we go to the next slide, we only have one ester really shown here, and that's at the bottom. Okay. So we know the O8 ending has to go in there. Right? Well, how many carbons are connected to the O8? No matter which way we go, we're going to get 2, right? Okay, so we'll make that a little bit more challenging in a second here. So our root name is a 2-carbon chain. Okay, it's sp3 hybridized outside of the functional group of the ester. So we'll do ethane and then O8, okay, because the O8 is representing the ester functional group. I haven't labeled the last 2 carbons. Those 2 carbons are now connected at the ester position. Because they're 2 carbons, I would name that ethyl. And I get ethyl, ethanoate. Yeah? Okay. This one, because it was symmetric, there were 2 carbons either direction, we actually don't get kind of a resolution on which part of the molecule should go with the O8. Should this have been a blue ethyl and then a red? Let's go through and do it that way. Does everybody get what I'm saying by that? Okay. Which part is getting associated with the O8? In this case, because they were both 2 carbons, it didn't matter. Okay. But what happens if I add a carbon? Well, now one is ethyl, one is propyl. Which of those gets associated with the O8?
The one attached to the double bonded carbon, oxygen.
The one connected to the double bonded oxygen. Why?
That's a functional group.
It's part of the ester, but so is the oxygen. Carbonyl is a higher priority. Okay? So if we made the adjustment that we now have here, we have a 3-carbon chain that is connected to the ester, so this becomes a propyl. It is a substituent on the larger structure of ethanoate. Make sense? Ish? Okay. Before we make that worse, let's go ahead and take a look at the next one to the right. Is that a carboxylic acid?
No.
Is it an ester?
You said it was.
Okay. Said it gets named like an ester. It's definitely not a carboxylic acid because for it to be a carboxylic acid, that K needs to be an H. Okay. It's not really an ester either because the ester, that K should be a carbon. Okay. But the nomenclature of esters is pretty much there's a substituent on the oxygen and name the rest of it. Okay. So what's the rest of this?
Pentanoate.
1, 2, 3, 4. You want to stick with pentanoate?
No.
Okay. What do you want to switch it to?
Butanoate.
Butanoate. Okay. What is the substituent connected to the oxygen? And we get
Potassium.
potassium butanoate.
Hard words to say.
Make sense? Okay. So let's double back to our ethyl ethanoate. Because if you reference that compound as ethyl ethanoate, you're going to get weird looks. Okay. Most organic chemists do not refer to that as ethyl ethanoate. What do they refer to it as? Well, that's clearly an acetate with a 2-carbon attachment, ethyl acetate. Note, we have that 8 ending. We're not calling it an O8, probably because acetoate sounds stupid. So we switched it up to acetate. Okay. Everybody agree? Clearly acetate. Somebody be smoking something. You really think that's clearly, obviously called acetate? What about that makes you go, yes? That looks like, it's going to be hard to say it without adjusting the ending appropriately. Acet. That looks like acetate. You got to throw the T in there to be careful. Okay, because the 8 is what makes it the ester. So what about looking at that purple part makes you go, that definitely looks like an ast.
I don't really get it, man.
When you look at this purple part, why does that say ACET? What about that purple part makes you say ACET as opposed to ethan?
The shape?
Because if I erased all that and said, draw the shape of ACET, you're going to draw that.
Arbitrary linguistics.
This is an arbitrary linguistic aspect. Okay? It's coming from a common name. Okay? ACS is very borderline on us. They explicitly state you are only responsible for IUPAC rules. Acetate is not IUPAC. Right? And yet, they will throw acetate on the exam. Okay? Why? It's so old as far as linguistics go, as far as chemical nomenclature goes, that it's become kind of part of the vernacular and we have to use it. Okay? Which sounds kind of weird, but if I ask you for the name of H2O, you're going to tell me water, not dihydrogen monoxide. Okay? So there are some compounds that are kind of just so ingrained into the culture that we deal with it. That group in purple is better referenced as an acetyl. Okay? Acetals show up all over the place. They really show up in this chapter, or these sequence of chapters. Okay, so you'll see reference to an acetyl group. It is referencing that sequence of atoms, 2 carbons and a carbonyl. Okay.
Phenol that we use for that?
I've seen AC show up. And in fact, you've seen AC show up. Right? We decided that that structure was a pain to draw out and typically gets represented as AC is coming from the acetyl aspect of this. Right? So we have seen it before. We just kind of ignored it because you weren't responsible for naming it. Now it shows up in esters, so we'll see that show up. Okay? So with that added context, what's the name of the top compound, top left? So ethanoic acid, you're going to get weird looks. Okay. We could reference it as an acetyl alcohol. We run into a little bit of issues there because that compound does exist. This is not acetyl alcohol, though.
Acetic acid.
It's acetic acid. So we definitely have the ACET letter prefix with the now ic acid because it's an acetic acid. Okay? Make sense?
So is it only these two compounds or all of them?
Anytime you see that grouping, two carbons in that carbonyl connected to a larger structure, okay, it will often get referenced as an acetyl. Okay, so it'll show up in a lot of places. Say that again?
How acid looks like the same acid.
Say that again?
Acid.
Oh, acyl? Yeah, the pronunciation is going to be challenging too. Acyl, as a group, you will also hear reference as an acyl group. Okay, that's hinting at this same thing. You're looking at a carbonyl connected out to something larger. The acyl is a larger category referencing any number of carbons connected afterwards. Typically, it's referencing CH3. Okay, if you hear reference to an acyl. But it can reference a sequence of multiple carbons. That's generic and not very useful. So typically, it's just the CH3. Last one. 1, 2, 3, 4, 5 carbons as opposed to 3, 4. So it must be a root of 5, right?
It's 4.
Why is it a root of 4?
Because you have your functional groups in that chain.
Your higher priority functional groups go to the 4 side. So we're going to get a bute for our root. We do have an alkene in there, so we're going to get a butene. Where does the alkene show up?
2.
Position 2. It actually didn't matter which way we numbered it. So butene, oic acid. Whoops. Theoretically, the 1 should show up in there. Sometimes it does, sometimes it doesn't. Remember, the carboxylic acid is the highest priority on our list for nomenclature. So by default, it'll show up at position 1. So because of that, it's often dropped off, kind of like aldehydes. And then what are our substituents? At position 4, we have an aldehyde. Aldehyde's lower in priority, so we have to call it a 4-oxo. At position 2, we have a propyl. Which comes first, propyl or oxo? Oxo, because alphabet. So we could get 4-oxo-2-propyl butene oic acid, butene oic acid. We'd still technically be missing something because you've got to deal with cis and trans around the double bond. So you would have to go through and evaluate priorities for those individual groups. I'd recommend cutting parallel first. This is higher in priority than that one. This is higher in priority than the hydrogen. Now cut. I totally cut them backwards. Watch. First cut this way, then evaluate your pieces. Then cut parallel. Where are the stars? They're on the same side of the second cut, which means, yeah, I always have a hard time with that. 2Z, 4-oxo-2-propyl butene oic acid. Kind of make sense? Okay. Some other nomenclature that I don't want you to necessarily stress about, but you should be aware of it because it's going to show up. What functional group do we have at the top?
Amide.
These are amides, so we could reference them as amides. We could call them ethanamides, right? Because they are 2 carbons. That's that weird, funny-looking group, though, because that's our acetyl, so we could call these acetamides. Okay? We have that methyl, though, that's floating around. Where's that methyl connected? to the nitrogen. I need to be extra specific about that. To be extra specific, what am I going to say? Because if I just say methylacetamide, it's not quite super clear. N-methylacetamide. What happens when I move to the next one where I have two methyls? N dimethyl acetamide. Kind of make sense? So if you see an N pop up in your name, all we're saying is that the substituent is connected to a nitrogen in the structure. That's the only reason. You can sometimes see N and N prime. What would be the difference there? They're two different nitrogens. So if your structure got really complex, you could have multiple nitrogens. You'd have to name where each one was. That becomes more challenging to deal with. Okay? We've already covered the acetic acid, but the acetic acid could get converted into this structure. What is this functional group?
Anhydride.
This is an anhydride. If we go through to make this, there's our acetic acid. There's where it mostly is in the product, right? Except what did I get rid of? A hydrogen. Where did I get those other two carbons and the oxygen? A second molecule. What did I get rid of? On the blue part? OH. Combine the H and the OH, what do you get? You get water. What did we call that functional group? And for not hydr or water. Okay? So what we're saying is not water. That's an anhydride because you removed water from the compound. Okay, so if we take two carboxylic acids and somehow remove the water from that solution, we can make an anhydride. Okay? So that's the core of this structure. We go through and highlight the color of that. This part is your anhydride. We could have any number of carbons running out the outside, right? Okay. So we would have to adjust our name on that. In this case, we'll call it. We could try a dimethyl. That's going to become problematic because you're not counting that carbon. Okay. So we could go with a diethyl because there's two carbons on each side. What was the name of this piece again? Acetic anhydride. Kind of doing a head nod towards where it came from, acetic acid. Okay. Typically, those show up as symmetric because they're the easiest ones to make when they're symmetric. They're a little bit more challenging to try and make when they're asymmetric. Okay. When it comes to synthesis, I think we'll really only expect you to make symmetric ones. Asymmetric ones may show up on a test just to kind of mess with kind of the chemistries a little bit. Okay. Kind of make sense? So those are our primary kind of new functional groups and a little bit on how to name them. With that, we can look a little bit at spectroscopy. What we're talking about as a functional group is typically our carboxylic acid derivatives. Because what we're doing is we're modifying the carboxylic acid by changing that OH into different leaving groups. Like an NH2. Like a carboxylate, like an alcohol, or even like a chloride. So all we're talking about doing is how do we modify that structure? Okay? So that means typically when we're looking at our spectroscopies, we're going to be looking at carboxylic acids and potentially some modifications thereof. Okay? When we look at an IR, what do we expect to see jump out at us?
Big, broad
We want a big, broad peak about 3,000, representing what? The OH. The OH typically shows up at 3,400. Why is it showing up at 3,000?
Because of the functional group.
Because of the functional group, yes.
Because of conjugation between the resonance brings it down.
The conjugation with that carbonyl. There's an internal resonance. That resonance weakens the OH bond, which means the stretching frequency at which it shows up drops to lower wave numbers. Okay? Which is something that's discussed when you talk about IR in Gen Chem or OChem 1. Okay? Most people forget it and just kind of memorize the patterns. That's fine. Okay? So a nice clean example would show this big broad range right about 3,000. Typically in that area we get some pretty clean peaks. We don't get this broad nastiness. So that broad nastiness is typically a red flag for the OH from a carboxylic acid. It is not a carboxylic acid. It's the OH that we might expect from a carboxylic acid. What else would we also expect to see? We need a sharp spike at 1700 to represent the carbonyl, the carbon-oxygen double bond, and there's that one. Okay? So this example that I've got up at the top and centered is a nice clean example because you're effectively seeing a beautiful OH, nice broad thing, just overlapping with the CHSP3s. Okay? It is very rare for it to show up so clean and beautiful. Typically, instead, it looks like the bottom examples. Okay? And I would argue the lower right is probably the better example of it. It just looks like not quite clean, it's broad. We're getting some weird stretching frequencies, like it just doesn't look right. Okay? The other one, it's big and broad. We're not really seeing a whole lot of CHs, okay? But it's at least this big broad range. Okay? So if you have a carboxylic acid, those are pretty big red flags that you've got one, okay, from your IR. Make sense?
Will in the case of conjugation, will that shift the CO double bond at all because that is showing?
As far as the CO double bond goes, yes, it shifts it. I would caution against doing anything with the CO double bond because the amount of shifting that you get there is minimal. Okay? And if you want more information with the carboxylic acid and that one shifting and why it doesn't shift that much, you can talk to me after class, but it is very, very minimal and it's a very dangerous one to assign because what is the exact value of that peak for the carbonyl? Pick any one of those. Tell me what the value is. If you can't tell me that value, okay, it's going to be very hard to say how much it shifted. At least with the alcohol, you're looking at a shift of like 400 frequency units. With the carbonyl, you're looking at a shift of maybe 10. Okay? That's a pretty significant difference as far as being able to interpret. Okay? So don't assign based off the shift of a carbonyl. Assign based off of a shift of an alcohol is fine, or the OH.
Does that change with another thing? So say you've got the double bonded and then that carbon double bonded to H2.
Yes.
And so
So this is one of the things that I will say with IR that becomes very challenging is everybody goes through and says, oh, well, I see a peak here, so it must be this. Usually in those ranges, a whole crap ton of things can cause it to shift around. Resonance is a big contributor. The structure itself, how big it is, where it's located in space relative to other functional groups, can also cause it to shift around. So don't overemphasize shifts or ranges or values in IR. When you look at IR, you should, within 10 seconds, no more, know what functional groups are there. Or know which ones are not there so that you can eliminate those answer choices. If you're going into it and being like, well, it's shifted by 10 and it's supposed to be 17, you've gone so far down the wrong path, you're in a problem. Okay? And just as a refresher, 1400 and lower, you probably shouldn't be touching because it's the fingerprint region, right? Everybody vaguely remember that? Okay, depending on your past instructors, I've had some that just go through and delete that whole area. Right? I think that is an awful idea because there's tons of information there. Okay? But be wary of that range and don't analyze in there unless you are absolutely forced to. Right? Like you analyze everything else and you're like, well, it gets me down to 2 answer choices. Now go into the fingerprint region. Does that make sense? Okay. I would argue for my sake and benefit, can I delete everything up there? There's not really anything up there. For me personally, I usually cut at 1600 and tend to ignore all of that. Okay? That is shifting way, way, way high with the fingerprint range. Okay? But the reason being is there's a lot of stuff that falls in that 1600 to 1500 range that's easy to over-evaluate. So I try to ignore looking at that unless I have to. Okay? So for me personally, it's almost like there's 2 fingerprints. Okay? Call it Mike's or Mike and everyone else. Okay? I tend to avoid that Mike range because it can be dangerous to assign in there. Okay? Kind of makes sense? Okay. With NMR, particularly HNMR is going to be the big one. With our carboxylic acid, we'll see a peak about 1200 at 12 ppms. Okay? There's this big statement of might show up. Why might it show up? The answer is officially up there.
Labial.
What the hell does that mean?
Something with the teacher.
Means the hydrogen comes on and off the structure. If the hydrogen's not on the structure, it's hard to see how the structure is affected by the magnet if it's not there. Okay? So because the hydrogen is very, very labile, meaning it's acidic, really, okay, it can be difficult to detect in the HNMR. Okay? This is seen with alcohols as well, because what you can do with an alcohol is put it in D2O, so deuterated water, and you can get a hydrogen exchange for the deuterium from water for the hydrogen in your structure, and you can see your peak disappear. Okay? So they're dangerous to look for. Typically what has to happen in a real spectrum is that if you zoom in at the baseline, okay, so really what you would see typically for a carboxylic acid would be something like that. You'd be like, well, there's nothing there. If you zoom in on that range, you end up seeing something like this. What's all the jaggedness?
The hydrogen popping off and going back up.
All that jaggedness is actually the baseline. That's signal to noise. When you look at an NMR spectrum and you see a flat line, okay, it's not a flat line, it's actually noise. Okay? It's the instrument picking up and not being able to decide, is that an actual signal or not? Okay? The big broad aspect we're seeing is due to the hydrogen being coming on and off, that it's showing up at a variety of different chemical shifts. Because depending on how far removed from the structure it is, it's going to change where it shows up. Okay? So when we zoom in, what we're really doing is trying to interpret the noise for the carboxylic acid. Okay? So it can be challenging to see in an IR, not IR, NMR. Okay? Typically when you see them, you'll be seeing clean NMR. Where would you not see clean NMR? In lab. Those of you in lab, you get to see it then. Okay? There was a hand.
That's just basically the noise floor being pushed up because it's...
Well, it's not that it's picking up a slight signal and that's causing effectively the noise to go up. Even the peaks that we're seeing that look like nice clean peaks, those are still noise.
Yeah.
It's just a question of where the noise is being picked up.
Floor, and then you get like...
Yep.
Okay.
Carbon NMR, you're not going to see any hydrogen because
Because it's a carbon.
it's carbon NMR. But we will see the carbonyl show up. Okay, the carbon-oxygen double bond usually shows up around 200 ppms. Okay, a little bit under. Why not exactly 200 like the aldehydes and ketones?
Because there's more resonance there and it bounces around.
resonance causing it to change the frequency a little bit. Okay? Questions? Cool. So, acids and bases. We're looking at carboxylic acids. So again, we need to understand how to differentiate between our acids and bases. Remember, when we talk about acids and bases in this class, and it's very particular to this class, we're referring to an acid as a Bronsted-Lowry acid, and we're referring to a base as a Bronsted-Lowry base. Most classes refer to acids and bases by their Lewis definitions. Those are too broad to make any use, okay, in my opinion. All right, so when we're looking at these, we're looking at an acid being a proton donor and a base being a proton acceptor. If we go through and look at our carboxylic acid, it becomes a good proton donor. Why?
It's an acid.
All right, we called it carboxylic acid, so that makes sense. It should donate a proton. Why?
It's very acidic.
Resonance can stabilize the charge on the oxygen.
We would look at the conjugate base, and that conjugate base is stable. Why is it stable? Resonance. Right? It is that resonance contribution. Right? So for acids, we typically look at the conjugate base, right? Because that's where we see some reactivity. Because in OChem, everything we do is about where are the electrons. The electrons aren't as obvious to manipulate or see in the starting acid, so we go to the conjugate base. If the conjugate base is more stable, that means the reaction is more likely to happen, which means we're producing more acid, or more H+. Make sense? What happens when we move to the other structure, a base?
You look for electrons.
Okay. Still the same principle. We're looking for electrons. Should I be looking at the conjugate acid?
No.
No.
Why not?
Has to.
Electrons. Can't see
Because
it.
you've already assumed.
If I go to the conjugate acid, I've actually hidden the electrons. Remember, OChem is about finding electrons and seeing how they move. When I'm looking at a base, I don't need to look at the conjugate acid. I can look immediately at the starting structure, because what does the starting structure have?
Lone pair of electrons.
The lone pair electrons. So I can now evaluate how those electrons react. Kind of make sense? Right? And that's kind of the confusion that the ACS really pushes, because when we talk about acid strengths, everybody goes, oh, you just evaluate conjugate base. But no, we evaluate the stability of electrons. It is easier to see the electrons for acids in the conjugate base. When we're looking at base strength, we're changing the definition so we can change how we look at it. We're still looking for our electrons. We find the electrons on the nitrogen. We want to see how likely those are to react. Kind of, sort of? Okay. ACS first semester is all about acid ranking. Guess what second semester is about? Base ranking. And if you just sit and memorize acid ranking versus base ranking, you screw them both up because they're going opposite directions. If you understand the definition of what an acid is and what a base is, you just apply the rules that we've talked about. Okay? And you can get them both right. ACS will ask a lot more base ranking base kind of questions on second semester because they already asked a whole bunch of acid ranking questions on the first semester. Kind of make sense? Okay. So don't fall into that trap. Nah. Okay. Acid base strength be altered. Okay. Stronger acid steals electrons from the hydrogen. Our electrons are pulled into the structure, meaning we're forming a more stable conjugate base. The conjugate base needs to be less negative. Okay? So stronger acids, stable conjugate base. Size. Which is going to be more stable? The bigger it is, the more stable it is, the stronger the original acid. Kind of, sort of? If we compare it across to bases, what happens? We want smaller. Why do we want them to be smaller?
It's less stable.
It is less stable. The whole point of the base is to donate electrons. The whole point for our acid is to keep the electrons. You're looking at two different definition systems, which is why the rules appear to change. Okay? You're still looking at the same basic's not a good word, the same core ranking system. You'll note charge isn't up there because at this point, charge tends to not be the answer. Okay? We're advanced enough that you stop losing that one. Okay? But charge does preempt all of these, followed then by size, electronegativity, resonance, and induction. You notice I did not include the last category, which is the catch-all for everything else. Okay? The catch-all for everything else can get tested on. It's just not fun to deal with and probably not worth your time. What are the things that would be in that catch-all? Molecular orbitals, hybridization, sterics, okay, substitution patterns. Okay? All of those things would fall into that category. Okay? So, we got 3 questions. Rank acidities. Go through, figure out which one's the strongest acid in each of those sets. Okay, we'll call it purple, red, blue.
Read all of them or just on paper?
Just on paper. So for that first one, what we're trying to do is identify the acidic atom. Okay, so in this case, we've identified the acidic atom as the one connected to the oxygen or to the nitrogen, and you ignored all of the ones on the carbon. Right? Why'd you do that? Electronegativity. Okay? So you do have an instinct to eliminate some of your answer choices. But one of the other reasons on why you could eliminate it is that, is there a difference between this and this? No. If there's not a difference there, you're probably not looking at it. Okay? So just looking at it, you should be using some of that kind of reflexive stuff to streamline your interpretation. Okay? Why is the circled one the acidic one? Oxygen is more electronegative than the nitrogen. Or as Mustafa, who walked out, suggested, it's the functional group. It's a carboxylic acid versus an amide. Which one do you think is the acid?
The acid.
Probably the one called an acid. Okay? Doesn't always work, but sometimes. The next one down, our red box, we've got a suggestion that it's the far right, and it's because of induction. Again, notice the patterns within this. We've got lots of similarities. We're looking at carboxylic acids showing up in all 3 of these, and we're looking at the same carbon chain through the backbone. So really what we're being asked to do is to decide fluorine versus hydrogen versus 2 fluorines. Right? Well, size and electronegativity are atom effects on where you removed the hydrogen. That's all oxygen in this case. We could look at resonance. They all have the same resonance, so we would now move to the inductive effect, looking at the fluorines being more electronegative than the hydrogens. They're going to withdraw electron density the most, so the outer 2 should be more acidic than the inner. The right one should be more acidic because there's 2 inductive effects as opposed to 1. Last one. Right, the suggestion was induction, that we have an electronegative element there. Right, this one becomes a little bit trickier to deal with. Why? There's resonance in there. We have to evaluate that resonance. Right? So how would we do that resonance? Remember, we're going to remove that hydrogen and have a negative oxygen. That negative oxygen, to be stable, needs to do resonance inwards. Okay? Meaning that carbon is what charge? To accept electrons from that oxygen, it would need to be positive. Is it being stabilized? Yeah, right? So the benzene is actually stabilizing that positive charge. By stabilizing the positive charge, what is it doing to that negative? Destabilizing it, making it actually less acidic. Everybody see that? Right? But so did the other one. Right? So you might say, well, there's no effect. Have we gotten to the nitro groups yet? No. Okay? So we've put a potential positive at that point, right? More resonance, which would put the positive here. More resonance, put the positive there, yeah? What happens with the other structure? And I could continue around. Why am I saying that purple positive is the most important one to look at? It's right next to the positive nitrogen. Is that a good thing? No. What does that mean about each of these arrows? They are less likely to happen. Okay? If they are less likely to happen, what does that mean? It's less likely to stabilize the positive. Keep going. That makes the right one more acidic. Okay? We are going to run into some conflicts here because we've got resonance suggesting this one. How close is that resonance effect?
Not very close.
That's not very close. That's a pretty long distance resonance effect. And we have the blue one being an inductive effect. Well, which one trumps? Resonance. So we might say, well, the resonance should be the answer. But the induction is closer. So which one wins out? That becomes a larger challenge. Okay? Typically, you won't get asked this. Okay? Where I would ask it on a test is for you to explain the difference between these. Okay? And as long as you're explaining within your logic set correct, I'd be fine with it. Kind of make sense? Okay? So you have to be a little bit careful, particularly when it comes to dropping carboxylic acids next to benzenes. Benzene has tons of resonance, and that resonance can distribute or allow electrons to be distributed over a very large area. Make sense? Okay. So, carboxylic acids, amines, and pH. What happens if a structure has multiple acidic functionalities and exists at different pHs? Okay, so the first thing we'll do is let's just switch that up, keep it simple. What would happen to this structure at different pHs? If I'm at a pH of 1, what do you guys think?
It's going to look like that.
I think you're going to end up with a diol.
I know where you're trying to go. Unfortunately, nope, you're going too far. It looks exactly like that. Okay? At a pH of 1, we're under acidic conditions. Okay? That is an acid functional group, a carboxylic acid. Okay? But if you're under acidic conditions, what's going to happen? It's going to keep the hydrogen on the structure. Okay? What if you were at a pH of 14? pH of 14 is now very, very basic, and what's going to happen? You're going to deprotonate. So we would remove that hydrogen. Yeah? When is that hydrogen removed? pH 10? pH 7? pH 6? 5, 4, 3, 2, 1.5.
Yeah, exactly. What percentage? That's
So-
going to be that's going to be in an equilibrium.
So
let's say,
yes, it is in an equilibrium, but ultimately what we're looking at is when that equilibrium shifts. Okay, so we're asking where's that shift point from being it mostly protonated versus mostly deprotonated. So we're at a pH of 7. Okay, and then I heard another suggestion, math. Yes and no. Okay. So what we're looking at is the balance between, and I'm probably going to butcher the equation, but we'll try it, the conjugate base and the starting acid. We want to know when that ratio significantly changes. Low pHs, we'd be at a small ratio. Large pHs, we'd be at a high ratio. Right? I want to know when that shifts.
When those are equivalent.
Okay, well, when are they equivalent? When does that happen? I know.
You need to give us some extra
Just
information.
Some extra information. Knight Rider? What the fuck? Baywatch.
You actually don't
Say that louder.
Hasselhoff? Henderson Hasselhoff.
Oh, great.
Henderson Hasselbalch. This is going all the way back to 152 with the Henderson Hasselbalch equation, which I'm pretty sure I'm going to butcher pretty badly here. And by pretty badly, I can't for the life of me remember if that should be a plus or a minus. Okay, and ultimately it can be plus or minus. It doesn't really matter, but then you swap those two. And I don't remember the pattern. I have always had to solve it. So,
You just had a test on this today.
oh, there you go.
It's this.
Is it really?
Yes.
Wow.
You're right.
Thank you. It's a coin toss, 50-50 chance. So I don't know how proud I should be about that. Okay? So what we're looking at is that exact shift. Well, when is that going to happen? When are those two going to equal each other? What happens if those two equal each other?
When the pH equals the pKa,
Okay? What happens if those two equal each other?
it turns into 0.
2 over 2 is 1. What is the log of 1?
0.
0.
So pH
When does that happen is when the pH equals the pKa. Remember how I said it might be useful to have some pKa's memorized? This would be one of those cases. That swap happens when we hit the pKa for the carboxylic acid, which happens to be not 7. It's 4.26 for acetic acid. So as soon as I drop lower than a pH of 4, I'm going to be largely protonated. If I'm higher than a pH of 4, I'm going to be deprotonated. Okay? For those of you moving into pharmacy, kind of important, medicine, all of that fun stuff, it's going to be important because it shows up in biochemistry and it dictates a lot of, say, drug interactions. If you drop a drug into the stomach, the pH is very acidic, which means you're going to put tons of hydrogens on the structure. That's going to change the solubility of the compound. Remember how we did the extraction labs back in OChem 1? Protonated versus deprotonated. Deprotonated is very water soluble. Protonated, not as water soluble. So if I give you a drug and you ingest it in your stomach and it becomes protonated, becomes less water soluble, what's the likelihood of that drug making it into your bloodstream?
Low.
Very low. More than likely what you're going to do is just excrete it. Okay? Because it's not going to dissolve into the water of your bloodstream. But if I give you the deprotonated form as an injection, now that makes it directly into the bloodstream. I don't have to worry about the pH differences. Okay? So depending how drugs are delivered, it's going to change how our body responds to and absorbs them. Okay? And that all goes through those subtle pH changes. Okay? The rule that I like to use, and I almost always forget it, it's not really a rule, but it's a derivative of the Henderson-Hasselbalch. is that if you are at a pH lower than your pKa, what does that mean? You're in the protonated state. You're in an environment that is more acidic than your pKa. Keep the hydrogen on. If you're at a pH that is higher than your pKa, you're more basic, which means deprotonated. pH of 5, it's going to be deprotonated. Is pH of 5 basic? It's still acidic. Okay? So it's all relative to the pKa of your compound. Not too bad, right? Yeah, easy. What's the question say? Multiple acidic functionalities. Thankfully, we would never have to worry about that in the real world. Say, like if we had an amino acid, like the mostly building block of our life. Like if we look at it, you get amino acids, nucleotides, and carbohydrates. Like a third of life as we know it is dependent on that stupid molecule. And that stupid molecule is fun because it has two acid-base functionalities. It has the carboxylic acid, which acts as an acid, and it has the amine, which acts as a base, which makes this one extra exciting because the acid and base functions react with each other. Okay, so when you change the pH, you have to be concerned about how each of those things are interacting. So let's drop it at a pH of 1. Okay? What would you expect to happen to the acid? It would stay protonated. What should happen to the base? It should be protonated. Is it protonated already?
Yeah.
No.
Okay. This is one of the challenging things with the amine. How do amines react? As bases. It's that lone pair electron that's reacting, not those hydrogens. Which means when we draw out an amino acid, that structure is inherently false. Okay? The nitrogen should be protonated. So I would get NH+. Okay? What happens if I jump to a pH of 12? We should deprotonate. Okay? Another way that we can track this here in a second. What would the charge be on this structure at pH of 1? Be a positive, right? Because of the nitrogen. And the acid is contributing no charge. Everybody see that? Okay. When we jump to a pH of 12, what happens?
It goes to negative.
We should deprotonate the acid because we're now at a pH that is greater than the pK of the acid. pK of the acid is 4.26. Duh, Mike, we just said that. Nope. No, it's not. What is the pK of the acid? 1 isn't a bad guess. It does go down. Why does it go down? Say that again. An inductive effect of the nitrogen withdrawing electron density into the structure. How much of an effect does it make? It's pretty significant. We drop to a pKa of about 2.5. Okay. So at a pH of 12, what happens to our hydrogen? It's removed, and we would have a negative oxygen. What happens to our amine? Also gets deprotonated, which means it loses its positive charge, and our charge is now negative overall. Okay. Where do those change? The pH equals the pKa. We said the amine was a base, so we could kind of skip that one because we've got a pKa for this one, right? Okay. So where are we going to switch? If I went to a pH of 3, what would happen? The the acid should deprotonate because we're at a pH that is higher than our pKa. What should happen to the base or the amine side? We'd have to know its exact pK. Do we really? We know that's supposed to act as a base. If its pKa was that low,
BKB is probably pretty.
okay,
It's also pretty.
probably wouldn't be the case, and we have that positive. Okay, so what's our overall charge? 0. So what is the pKa for the ammonia or the nitrogen? That becomes tricky because when you look up the pKa, they tend to give you two different pKa's. They tell you the pKa for the nitrogen or for the ammonia or let's just say a nitrogen is 35. Are we ever going to hit a pH that's going to align with that? No. So what the hell? When we talk about a pKa for the ammonia being 35, what are we referencing?
The conjugate base.
We're looking at ammonia acting as an acid. We're going to NH2 minus or the N minus. That's not what we're talking about the ammonia acting as. Why not?
Because we're talking about ammonia acting as a base. Like, we're not talking about
Where does our amino acid exist? 80% of our life?
in our blood.
Water, right? pK of 35, we're going to run into a massive leveling effect issue. We can't get amide in our bodies. It's not going to exist. Okay? Water will protonate that. Okay? So what we're talking about when we talk about the pKa for the amine is not for the amine, but for ammonia, and that's about 9. Okay? So the pKa for this one is about 9, which doesn't look clear at all. Let's erase some stuff. There we go. So if we jump to a pH of, what do I want? 8, what would happen? It's the same as 3. If I jump to a pH of 10, it's the same as 12. Kind of make sense? So what we're looking at is how pH levels can affect our overall amino acid structure. Is that a big deal? Just like with the drugs, if we change the pH, we change the protonation states, which changes the solubility. If your blood was constantly changing pH, guess what happens to all of the proteins, amino acids, and other fun things in there? They're all going to be oscillating their structural effects, going from soluble, insoluble. You'd be having blood that's liquid in 1 second and solid in another. That's really bad, particularly considering that when you exhale and inhale CO2, CO2 changes pH levels in water. That would be a really big issue because we generate CO2. So what did life do? Found a way by doing what?
Buffers.
Making buffers that minimize those pH fluctuations. Okay, so that it maintains a relatively constant pH. And if we travel just outside of that range, we get all sorts of horrible things. Okay? So, you got to take biochem, welcome to that. Okay, my favorite example from this, see, did I actually put it up there? I didn't put it up there. Okay? So we'll ask it as a question real quickly. What amino acid is that?
It's on the top.
Is that aspartic acid?
That says aspartic acid. That one's not actually aspartic acid. The aspartic acid is a note for me.
I don't know. What is it?
I think it's glycine.
Oh, so this is a...
I always get glycine and alanine. I think it's alanine confused.
I think it's glycine.
It's glycine or alanine. It's one of those two.
I think alanine is a methyl.
Yeah, that's the issue. It's a hydrogen versus a
It's
methyl.
a glycine.
That's glycine.
Again, 50-50, so I don't know how great that is.
Great.
So, glycine. What if we switch to aspartic acid? This one I'll probably butcher.
Perfect.
What's the issue with aspartic acid?
It looks like a snake.
It's got 2 carboxylic acids.
We have another acid group, which means
I like the cutie.
another pKa that's going to potentially affect solubilities. Okay? Why does that become fun? You would have to be able to know what glycine looks like and how it responds in the solvent, okay, according to pHs. Now that you have to know that, you have to know that glycine is a lot of letters to write. So you would have to know that GLY makes more sense. GLY is 3 times too many letters.
So we just use G.
So you would have to be able to look at a sequence of just a bunch of gibberish and be able to say, what is the charge on that amino acid? And what they're asking is, what are their side chains? Do those side chains have a pH effect? What would happen to them, protonated or deprotonated? My favorite example is this amino acid. And unfortunately, I ran out of space. Because you're responsible for interpreting that 1-letter code out to the structure to recognize how it's going to be affected by the pH. Okay? And so what you would be asked is, what is the charge on that amino acid or that protein?
I like that protein too.
I was going to point out that if you ever had that on the question, that would be scary.
It is a question I ask in biochem. Okay? It's a typical question in biochem. Okay, so you're responsible for knowing what all those amino acids are. Why? Because that's what biochemistry is supposed to be about.
Is that not a difficult question in biochem?
It usually causes a lot of problems. Why does it usually cause a lot of problems?
So many. You're abbreviating a lot.
There's a lot of abbreviations in that information. You're looking at pH changes and how they affect structure. So ultimately that relies on your OChem knowledge. How well did you do in OChem? If you didn't understand the patterns that were addressed in OChem, you've got some more memorization to do. Maybe you didn't like OChem, so instead you decided to rely on the Gen Chem, and as Mustafa said, that meant you had to go back to the math to be able to solve it from 152. So pretty much any way you slice it, that question becomes very difficult and it causes a lot of people to flounder. And ultimately all it is do you understand the difference between an acid and a base? You just apply it. Okay? With that, while I would like to keep going, I think we kind of had to stop.